We are in chapter 18, talking about sampling distribution models for proportions. I set this up pretty well yesterday when we started talking about the M&M activity. We took a bunch of different sample sizes, we put all those samples together, we started looking at the models, and you saw as the sample size increased that it became closer to a normal model. We can do stuff with a normal model, right? We know how to draw a normal model. We know how to find probabilities within a normal model. We know some stuff about standard deviations, things being unusual, plus or minus 2 or 3 standard deviations above, below the mean, right? So we know stuff about a normal model. So if we had that at our disposal, that would be a good thing, okay? And that's why it's a good thing here. So I kind of said all this yesterday, but it says no longer is a proportion something we just compute for a set of data. So proportion doesn't have to be just a number anymore. It's a random variable quantity that has a probability distribution, and we have a model for that distribution. And so we call that the sampling distribution model for the proportion. With a model, I could do stuff. With just a proportion, I can't do anything. So on some of your projects, you found, some of you had to find percentages. Like someone in first period, they did an experiment. And so they found the percent of people that did whatever in their categories, right? Well, so that's all they could do. But now we could kind of look at that, maybe determine some other things. We can do something with it. The best part about the sampling distribution model for proportions is that you only need 2 numbers. And you can do everything you need to do. You need P, the true population proportion, so not what you came up with in your sample, but the actual population proportion. And you need N, your sample size. If you have those 2 things, then you can do everything we would need to do. With those 2 numbers, we can check all of the conditions / assumptions, and we can find the mean and standard deviation of the model so we can actually use the model. So that's all you need is 2 numbers. That's awesome. Okay? So for this model, it's a normal model. We established that yesterday. The mean of that model is just P. That's all it is. All right, so the mean for the sampling distribution model is just P. That's where it should be centered. That should make sense. The standard deviation is the square root of PQ divided by N. Now, that's on the AP formula sheet. That's awesome. You will see in the next few chapters where we're going with all of this. And on the back of that formula sheet I have for you, there's a list of inference procedures. The means, as you've seen with like random variables, remember random variables, you could just like multiply the mean by whatever you wanted to. You could add or subtract, that kind of stuff. There was no tricky rules with those. Same thing with all these inference procedures. The means are going to be pretty straightforward. So you should be able to identify them pretty quickly. Like this one's the true population proportion. Got it? Yes, it's a failure. So P is success, Q is failure. Right there, the complement of each other. But so on this formula sheet, you have these tables. And there's one for single sample and one for 2 sample. We'll do 2 sample later. Right now we're worried about single samples. Okay, we have 1 proportion. That's all I'm worried about. And you see there's a place for sample mean and sample proportion. We're doing proportions. And it says standard deviation for that statistic. There it is. Right? It's a little bit different just because the Q that I just mentioned is not a standard notation. That's what our book uses. So on the formula sheet, you'll see the square root of P times 1 minus P over N. That's the same thing. Right? Okay. But if you have P, and then you find the standard deviation, then you have a normal model. You can figure out standard deviations from the mean. You can draw it. You can find probabilities. We can do lots of stuff with that. And then hopefully yesterday we talked about this a little bit too, but the model quantifies the variability. So it tells us how surprising any sample proportion is. We have a model, and I'm looking for a specific value, some specific proportion, and it's so far away from the mean, I've got standard deviations to quantify that now. It's 4.5 standard deviations above the mean. It's 2 standard deviations below the mean. It's 1.5 standard deviations above the mean. Right? Now I know how variable it is. So now I might know how unusual something is. That's why this model is important. Now I can do stuff. Okay? In the questions we do today, I think you're going to see a similar pattern because they're all going to get pretty repetitive. In general, this is what you need to do. They're going to give you a true population proportion, or they're going to give you a scenario where you can figure it out, like coins, dice, that kind of thing. They're going to give you the sample size, and they're going to ask you questions along these lines. They're going to ask you to check conditions and assumptions to make sure you can actually use the normal model. You can't use it unless it's met. Okay? They're going to ask you to find the standard deviation of the model. We can do that now. We have this formula. They're going to ask you to use the 68, 95, 99.7 rule to draw it and talk about it. They're going to ask you to find probabilities based on the model, which we can do with our calculator. Right? It's all this stuff that we have done before. We're actually pretty good at, but now it's just in a different context. This is where we're going with all this, and why it's so important. In chapter 20 and 21, we're going to start talking about our first hypothesis test, which doesn't mean anything to you right now. That's fine. But if you recall yesterday from our little activity in class, at one point, one of the groups got a proportion of orange M&Ms that was way high. It was like 0.6. And the rest of them all day had been like between 0.0 and 0.5-ish, right? I mean, 0.4. No one had really gotten one that large. Well, how are we to know if that's a significant result or if that means there's more orange candies in their bag of M&Ms or whatever? We can't tell that. We don't really know what to say. We can say it's a certain amount of standard deviations above the mean, but we want to know if it's significant. Like, is that an important thing? That's what statistics all boils down to. You do everyone that's out there in the world doing stuff with statistics has done some sort of project or some sort of study, and they're trying to figure out if their results are significant. So there's tests that tell you, yes, it's significant, no, it's not. All right, so this model, we're going to need to know so we can do the test. We can say, oh, this is significant, or no, it's not. So that's where we're going with this. We're going to keep using the same idea for the next few chapters. Okay? So here are some questions. These are on page 432 or 433, one of the two. I'm going to do most of them with you, and then I'll give you the assignment. It says, in a large class of introductory statistics students, the professor has each person toss a coin 16 times and calculate the proportion of his or her tosses that were heads. Easy enough. The students then report their results, and the professor plots a histogram of these several proportions. So just like you did yesterday, but with coins instead of M&Ms. All right? Everyone does it, and they put it all together in a model. On part A, what shape would you expect this histogram to be, and why? So an important question there is to think about the probability of getting heads when you flip a coin. 50%, 0.5. What's the probability of getting tails when you flip a coin? 50%. So because of that, because it's a 50-50 result, what do you think the histogram is going to look like? Unimodal and probably symmetric, right? A lot of people are going to get close to that 0.5 mark, you know, out in 16. Some people are going to get less than that. Some are going to get more than that. It's all going to even out. It's going to make this nice unimodal and symmetric idea, right? So I would expect a unimodal, symmetric, and that's because of the 50-50 probability situation here. Now, if it wasn't 50-50, one of your homework problems tonight is going to ask you a similar question. It's not 50-50. It's talking about M&Ms. So is it going to be symmetric necessarily? No. But just because of the nature of this question. Okay? Questions about that? Part B, where do you expect the histogram to be centered? Where should it be centered? 0.5. But we're talking about proportions. So we're not talking about the number, we're talking about proportions. All right. So 0.5. We're expecting the hysteresis centered at 0.5, 50%. That makes sense. How much variability would you expect among these proportions? Before today, we really don't have an idea of how to do that. But how can we measure variability now? For the standard deviation, we have a formula for that. So the standard deviation is the square root of 0.5 times 0.5 over, what's our sample size here? 16 points. So, will someone do that with me real fast? .125. Alright, so now I know that within one standard deviation of the mean, I would expect a proportion of 0.375 to 0.625, right? And I could go on to about 2 standard deviations or 3 standard deviations. I now have an idea of how spread apart the data is going to be. One standard deviation would be between 0.375 to 0.625, right? 0.5 plus or minus 0.125. Okay. So I could talk more about standard deviations now because I know what it is. Now in part D, it says explain why a normal model should not be used here. Okay. So we talked about assumptions and conditions yesterday, and there's 3 conditions that have to be met. It has to be random, no problem here, it's flipping a coin. It has to be less than 10% of the population. In this case, the population is like all possible coin tosses. It's kind of arbitrary and not necessarily necessary in this question. But we still have to have success failure, right? So NP has to be greater than or equal to 10, and so does NQ. They'll be the same in this case because the P and Q are the same. But 16 times 0.5, as Trent has told us many times today, is 8. So 8 is not greater than or equal to 10. It's you too. So the success failure condition is not met. Which essentially means our sample size isn't large enough. And so we can't use a model because we're using too small of a sample. Does that make sense? Yes, we need to have more coin tosses if this is going to work. Questions about what we talked about number 5. The next 2 questions keep going back to this coin toss situation. We good? Okay. On 7, it says suppose the class in exercise 5 repeats the coin tossing experiment. The students toss the coins 25 times each. Use the 68, 95, 99.7 rule to describe the sampling distribution model. That means we have to do what? We got to draw it, which means we need what 2 things? A mean and standard deviation. So our mean is still what? 0.5, probably mean heads. Is the standard deviation still 0.125? No. Why? All right, we changed the sample size. So 0.5 times 0.5 over 25, which ends up being 0.1. So I'm going to try really hard to make a bell curve. I mean, that could have been better, but it's okay. So my mean is 0.5, which standard deviation is 0.1, so I've got what, 0.6, 0.7, 0.8, 0.4, 0.3. I'm not even even, I apologize. We need to label it. Now, I'm going to write a sentence because I want to make sure we understand what this means. We're talking about proportions and actually numbers like we had before, so it makes it kind of tricky. And it's a sampling distribution model. So it's not just one sample. This is all the possible samples of size 25 flipping a coin. So I would say, just for example, 68% of samples of size 25 would have a proportion of heads between 0.4 and 0.6. So before we did this, we talked about like actual number values. There's always like one thing, right? We had actual, we didn't have proportions at the bottom. We had like integer values generally, right? We were talking about maybe 68% of all students who wore green shirts to school or whatever, and we had actual numbers of students. Here it's a sampling distribution model, so remember that's all the possible samples of that size, all put together. That's why I have that sentence. Does that make sense? Okay. On part B, it says confirm that you can use a normal model here. So you have 3 conditions we need to check. We have to write them out. One of them is what? Random. Are they random? Yeah, it's coin tosses, right? So we're going to assume those are random. It doesn't say otherwise. So it's say about being random because they're just coin tosses, each side is equally likely, whatever. What's another one? Less than 10% of the population, but that is going to be weird in the situation because your population is coins. So it's not actually necessary. If you don't check that one, like on the AP exam, they probably wouldn't want you to because it doesn't really make sense. And the last one is what? 10 successes, 10 failures. So MP has to be greater than or equal to 10, and NQ has to be greater than or equal to 10. Luckily, we're doing coin tosses, so both of those are going to be the same. So you have 25 times 0.5, which is what, 12.5? So 12.5 is greater than or equal to 10. Success failure condition is met. So all of our conditions are met this time. Everyone good so far? On part C, they increased the number of tosses to 64 each. Draw and label the appropriate sampling distribution model and check the appropriate conditions to justify your model. I'm going to go on a limb and say you guys are good with drawing the model. But let's just talk this through real fast. If we change your sample size to 64, does the mean change? No. Our true proportion is still 0.5, right? Our standard deviation is going to change. Is it going to get smaller or larger? Smaller, right? When we had 16 coins, it was 0.125. When we had 25 coins, it was 0.1. When we do it again, it's going to get smaller. It's 0.0625. Okay? Which makes sense. We saw that yesterday. As you increase the sample size, your histogram gets closer together. Your spread is less, right? Your standard deviation is smaller. It makes more sense. And then it said to check the appropriate conditions. Well, if all the conditions were met for part B, they would still be met for part C, but your NP and NQ would be different numbers, and you have to show that. You'd have to do 64 times 0.5, which is 32, not 12.5, right? But it would still be met. So all the conditions are still good. So D says explain how the sampling distribution model changes as the number of tosses increases. We just talked about that. The mean stays the same because P stays the same, and your standard deviation decreases. Right? Does that make sense to everybody? Yeah? Okay. One more question about the coin tosses. One of the students in the introductory statistics class in exercise 7 claims to have tossed her coin 200 times and found only 42% heads. What do you think of this claim? How we talked about before, how do we talk about if claims are unusual or not? we talk about standard deviations. So I know my mean is 0.05, or sorry, 0.5, not 0.05. But my standard deviation is going to be different here because I have a 200 times and not 25 or 64. So 0.5 times 0.5 divided by 200. And you get 0.0354. Okay. So someone have the calculator because they're going to do some calculations for me. 42% is below the mean, so I'm going to subtract. Okay? So if I start at 0.5 and I subtract 0.0354, what do I get? Alright, so that is one standard deviation below the mean, right? And so then I would take 0.4646 and I would subtract 0.0354. 9 what? So that's 2 standard deviations below the mean. And so if you do that one, you get 0.3938. So that's 3 standard deviations below the mean, right? Where does our 42% fall? In here, right? Okay, so there's 2 appropriate responses because there's no set way of saying any of this. We've talked about it both ways. I said that 42% heads is not unusual because it's within 3 standard deviations of the true proportion 0.5. The other appropriate response is 42% seems a bit unusual since it's outside of 2 standard deviations below the mean. There isn't an accepted way of saying 2 or 3. It's 2 or 3. It's like a 2 or 3. I don't know. It's kind of a gray area. I said it was not unusual because the standard deviation is so small, right? 0.03, that it's still within the 3, so it's still in that 99.7%. So I'm okay with it. I don't think it's unusual. But again, later in this unit, when we start talking about actual testing, there will be a set way to determine that it's significant or not. It's not just going to be this arbitrary, it's 2 or 3. All right, so we're getting there. We're getting to where we can get rid of that gray area. We can say, yes, this is significant, or no, it is not. Okay, we're getting there. But questions about number 9? I would accept 2 answers. I would say, sure. I would say either it's within the 3 standard deviations from the mean, so it's not unusual, or I would say it's below 2 standard deviations from the mean, so it is unusual. It's kind of a gray area. That's why I said later in this unit we're going to talk about we can figure out yes or no. Okay? Other questions about the coin toss questions? All right, let me do one more. And we'll kind of talk through some of the other ones. That'll be done. All right, on 15. Based on past experience, a bank believes that 7% of the people who receive loans will not make payments on time. The bank has recently approved 200 loans. So what do they give us in the prompt that's probably important? We're going to say 0.07 is P, the true population proportion, and our sample size is 200, right? That's probably important. On A, what are the mean and standard deviation of the proportion of clients in this group who may not make timely payments? The mean is easy. What's the mean? 0.07. Just 0.07. And then, what is the standard deviation? Right, 0.07, 0.93, divided by 200. Which is 0.018. There you go. Remember we're talking about proportions. So some of you guys are really quick to jump to people, number of people, clients. We're talking doing that. We're talking about proportions of people. So be careful. All right, on B, what assumptions underlie your model and are the conditions met? So yesterday, this is a good distinction. We talked about 2 assumptions you have to make and then 3 conditions that back up those assumptions. All right, so we have 2 assumptions. I almost abbreviated that and that would have been really bad. Okay, I thought that through. Okay, first one is what? Trent just said it. Independence. What means we're assuming that every client is independent. And then what's the second one? That's one of the conditions. The second assumption is that your sample size is large enough. The condition that backs it up is the success-failure condition. All right, so we have 2 assumptions, and there's 3 conditions that back those assumptions up. You can't actually do anything to show independence or your sample size is large enough unless you show the conditions. All right, so 3 conditions. One is random. That backs up independence. And we are going to say that we assume the 200 clients are a good representation of all clients. If it's a good representation, then that satisfies randomization, right? What's another condition? Success, failure, there's one more. 10%. So 200, hopefully, is less than 10% of all clients. That also backs up independence. If you got into a sample size that was too large, then those events may or not be independent. And so then the last one is success failure. So we have 0.07 times 200 and 0.93 times 200. And you should get 14 and 186. That backs up that the sample size is large enough. We just say the success failure condition is met. Yeah, a lot of the times you're just checking the 3 conditions, but it's important to remember there's 2 assumptions that those are backing up. You can't show anything just by assuming those, but you can show some other things that back those 2 assumptions up. Does that make sense? Yeah. Success failure condition. All right, and then on part C, what's the probability that over 10% of these clients will not make timely payments? We can use a normal model. We just told all the conditions were met, right? If we can use a normal model, how do we find probability? Use your calculator, right? You find what that section would be. So picture this, because you guys need to practice this. We talked about the free response question on the AP exam. You need to draw something really quickly to make sure you hit all of those marks that they're going to want. So really quickly, your mean is 0.07. Your standard deviation is 0.018. So that makes this 0.088. Right? That shows one standard deviation from the mean. Right? We're looking for probably the 10% will not make timely payments. So 10% is somewhere in here, right? And we're going to infinity. By drawing this model, I have shown, 1, it's a normal model with a mean of 0.07 and a standard deviation of 0.018. 2, I know what the lower boundary is, and I know what the upper boundary is. And then you're finding the probability based off of that information. Okay? So what do you use in your calculator? Normal CDF. So you would be going from 0.1 to infinity, which, let's talk about this real fast. We're talking about proportions. So what really is infinity here? 1. And then we have from mean of 0.07 and a standard deviation of 0.018. Yeah. I'm just saying, in general. Okay. So, if you wrote it that way, you could also label these. I prefer you draw the picture. But you could also label that. That's just less appropriate, I feel. Anyway, in doing all that, your probability is... .018 is your standard deviation. Yeah, don't forget, normal model is a distribution, right? That's why it's on the distribution menu. So if you get lost, find your calculator. If not, remind me later this week or next week, and I'll remind you how to use the catalog button in your calculator. So you get a probability is 0.408. So there's a 4.8% chance that more than 10% of their clients will not pay on time. 4.8% chance that more than 10% of their clients don't pay on time. Does that question make sense, though, what they're asking you to do? Well, a 4.8% chance that more than 10% of their clients don't pay on time. All right, I'm not going to do the other two examples, but I just want to talk them really quickly. On 21, they're giving you similar stuff that we just talked about. They say they're polling, the local newspaper's polling some people to talk about school budget, 400 voters, 52, they think 52% actually support this budget, whatever. But they say, what's the probability the newspaper sample will lead them to predict defeat? What percentage would show defeat? Less than 50, right? That would show defeat. So when you're doing your probability, you would be going from negative infinity to 50. All right, so be careful about what they're asking. Also, on 25, it's about smoking and non-smoking in a restaurant. And this is about 60% of the customers demand a smoke-free area, and a new restaurant with 120 seats is being planned. How many seats should be in the non-smoking area in order to be very sure of having enough seating there? Well, you have a proportion and you have a sample size. What do we say? How do we determine when things are unusual? We talk about standard deviations, right? So if we were going to be very certain, we would find 3 standard deviations above the mean, and that should be plenty, right? Just, you guys know all the stuff about normal models. You just got to come back and use it, okay? Your assignment is page 433, 6, 8, 10, 16, 22, and 26. And I want you to read, skim, whatever, about sample means, because this pretty much happens all over again when you don't have a proportion. What if you have a mean instead of a proportion? Because proportions only work for categorical data. So what about quantitative data? So I want you to quickly look over so you have a good idea about what's going on tomorrow. Page 419, the very bottom of that page, to 422, the top of that page. Just skim over that.